So the context of this video is to talk about the state machine diagram. It's one of the 9 types of SysML diagrams. It is a behavioral diagram. And so we'll jump into some definitions first and some examples that kind of show how transitions, guards, states, how it all works. And then we're going to go to a real world example, our oscillating fan. So for some quick definitions, we have states and pseudostates, such as initial state and final state. We will talk about in detail the orthogonal state. And so each of these are states: Alpha, Bravo, Charlie, Delta, Echo, Foxtrot. Those are states. These are all pseudostates. And we have guards, that X is greater than 5. That is a guard. And we have transitions. All the arrows are transitions. The signals are shown, and they are signals that are the trigger to transition from one state to another. And then we have other effects where you can change the value of X. In this case, X equals X minus 1 when it goes over from Delta to Charlie. And then we have some history, shallow history and deep history. And we will explain that as well. So we'll run this in simulation. We have 2 options. It's either run or run with context. We'll just do run first. And that's just running the behavior with no actual block behind it, no structure behind it. So we push play here and the behavior will start. And we start into the alpha state and the Charlie state. And you see it says alpha and Charlie here. And then we can do signal 1 and it will change. And it asks us the question, is X greater than 5? It will say yes. And we can do signal 1 again and it will go to Foxtrot. Signal 2, signal 1. And now we'll do signal 4 to kick it out. So the normal transition back would be signal 1, which will restart everything. So there's no remembering, there's no history. So it goes back to the start and it starts back with Charlie. So then the next example will be the shallow history. So we'll go to signal 1, we'll say yes. If we say no, then it just won't go. So see? And then if we say yes, then that's the guard right there. And we'll change it to Foxtrot. So we're a Delta, Foxtrot, Alpha, Delta, and Foxtrot. And then we'll do signal 4. And then this time we'll do signal 2, which is the shallow history. And you see that it remembered that we were in Delta, Alpha and Delta, but it didn't remember that we were in Foxtrot. The deep history will remember that. So if I just go to signal 1 again, so now we're in Alpha, Delta, and Foxtrot. And now I'll go back to Bravo. So if I do signal 3, it's going to remember the deep history, meaning like the state within a state. So signal 3, and it remembers that we're at Foxtrot. So now we will rerun this with context. And the difference is that it's running with the structure, and that we have a value property with this structural state machine diagram block of X, which has an initial default value of 6.6. So when we run this, now instead of asking us, is X greater than 5, it will just know. So if we do signal 1, it doesn't ask us anymore. And then we have this other effect right here. So if I hit signal 3, you see that it went from 6.6 to 5.6. So I'll do that a couple more times, and then we'll realize that it will not satisfy that X is greater than 5. So we're going from Charlie back to Delta using signal 1, go back that way, and then we'll use signal 3 again. So it'll drop from 5.6 to 4.6, signal 3. So we're at 4.6. Now when I go to signal 1, nothing happens. Like I just selected it, but nothing happens. So I can retype in like 10 and then go back to here and do signal 1, and now it will allow me to go to Delta. The last thing I'd like to demo is the entry, do, and exit behaviors. So to do that, we will create an activity diagram, and we'll just call it example activity. And we'll just basically make it have some logic here. So I'm just adding guards here so that we know how it flows. So basically it'll go down here and evaluate x and say if x is greater than 8, then complete, else then add 2 to x. It's going to loop a couple of times. It's going to happen. So now that we've created that, I will kind of show it here, and we'll make it the entry activity. You can just drag and drop the activity like this, and what that does, it actually kind of makes this nested configuration, which I'm not a huge fan of. So the other way to do it is you can go into the spec window and you can scroll down and then you can drag your example activity into the entry. There we go, behavior element. And what that's going to do is now you don't have that nested situation. So now we'll run this with context, and upon entry of the state, it is running this example activity. And you can see that it looped a couple times and added 2 to x until it was greater than 8. And then it completed, so we can run the rest of our state with no issue. So now that we came back to the Charlie state, remember it took away 1, but then since we entered the Charlie state, it automatically did that activity. Now what we can do is change it to an exit activity. So I changed my properties to standard just to make it easier to see. And then you can just drag it from here down to exit, and you see it changed to exit here. So now we'll run that with context, and you see it jumped into Charlie but didn't run it. So it's only upon exit. So if I hit signal 1, now it runs it. So if I come back, so it still didn't run it, but if I hit signal 1 again, it runs it. So it only does it upon exit. It's important to note that the entry and exit criteria are uninterruptible. So if I add signals or if I have any other triggers that are sent during the time of entry or exit activity running, it's going to wait until that activity is complete before continuing. The do activity is different though. So it is interruptible. So if I change this and move this to the do, what I can do is run it, and then I will immediately do signal 1, and you see how I interrupted it and it stopped it when it was still at 6.6. So if I go back to Charlie state, it's going to start it. Oh, it did it once, and it was about to do it a second time, but I didn't let it. I sent another signal, so it added 2, but it didn't add 2 more. Didn't do the loop twice. So the do state is interruptible and the entry and exit are not. That's the biggest difference. In this example, we will focus on the state machine diagrams that were created in this oscillating fan example. We've got 2 different options. One's more refined than the other, and it kind of goes through how we build out state machine diagrams and how we would find problems with them and then refine them further. So our prerequisites to both of these state machine diagrams is basically the problem domain, which is we've already selected a system of interest. So we've started with our user needs that you see here, and then we've created a use case diagram to figure out our cooling system of interest, use cases, and the actors that are associated. And then we kind of brainstorm some solutions for possible cooling systems. And we down select to the oscillating fan as our system of interest. So moving on to the state machines, we have decided now that our oscillating fan is our system of interest. So we do a first pass at creating a state machine for our system of interest. So I'm going to go ahead and run this state machine in simulation by pushing the play button here. And then we've got our behavior down here, and there is no structure associated with this state machine, so we only see the state machine. So when we push play here, it is actually going to run the behavior itself. So we see I ran it, and it is going to the unpowered state. And then we have options of how to change the states. These are signals that plug in and remove power. So if I plug it in, it will transfer to the powered and off state and the powered and oscillate state. So we can also just go forward and push low speed signals, medium speed to transition the states that are in parallel, as well as remove power, and then plug it back in, and now it starts back at the off and oscillate state. So one thing to note is I've got this oscillating fan, this top one selected. What that means is that my trigger, all of my triggers that are available, all of my signals that are available will be shown here. So right now, there's no way for me to change from the off directly to the high speed state. So if I just click this high speed, nothing happens. Or if I hit the medium speed, nothing happens. So it shows me every single signal that is available. But if I click on this second one, this one down here, then it will only show me the signals which will affect the behavior. So if I hit low speed, it will then show me medium speed or off. So it will only show me the states that, or the signals that can affect the behavior. So we might notice that there are some issues with this state machine, and so we'll go ahead and stop it. So our original system of interest has a knob down here, which is 0, 1, 2, 3, or off, low, medium, high. And that's why this knob, you can't just go directly from low to high, because the knob mechanically only allows you to go one selection at a time. And then the oscillate and static state is the pull knob that is behind the fan that allows it to go back and forth. So you push it in and it oscillates, you pull it out and it is static. So it's just another mechanical mechanism. So all that to say, you should be able to, let's say, push in or pull out, be in the static mode for the oscillating fan, and then you should be able to have it in the high speed or number 3 setting, and then plug it in, and it will be static and high speed. But this state machine does not allow that, and I'll show you. So if I push play, it starts me at the unpowered, and if I plug it in, every time I plug it in, it's going to go to off and oscillate. So it doesn't allow you to start with high speed and static. So even if I go to high speed, or if I go to low speed, medium speed, high speed, and then I change it to static, now if I remove power, I was at the high speed static state. So if I plug it back in, what should happen, if the state machine were correct, it would go back to the high speed and static state. But instead, it like resets to off and oscillate. So we're going to have to modify this current state machine to work for how the actual system of interest works. So now what I'll do is I'll pull up option 2. This is the more refined state machine. It has a lot more features. I went ahead and put version 1 on the left and version 2 on the right. On version 2, I went ahead and suppressed the internal activities just to make it more clear. You can easily remove those from view by just clicking that little minus sign. So you can refer to this when you're trying to understand how things have updated. Note that version 1 doesn't have any internal activities to show, so only version 2 is actually hiding these internal activities. So we'll just go ahead and run this state machine with context, which means with the associated block. That's what that little icon is. And we'll show how it works. So we'll push play here, and it looks like we start in the unplugged, zero, and oscillating positions, and then we can just click down. So right now we have all of our options, but if we click down to Oscillating Fan 2 right here, you'll notice that we only have the options that are available to us. So we'll go to the high speed, medium speed, and the static state. So now if I turn this to the, if I remove power, and if I plug it back in, you can see that I still remain at the medium speed static state. So now it's the state machine is no longer dependent, or it never resets like we had here where it reset to the off oscillate state. So that's great and as intended. So the next thing to understand is we have entry behaviors for each of these states, and you might ask, what is that? So what you can do is you can select on this fan again, and you'll notice as we switch the states around, so if I go to low speed, the RPM actually changes based on what speed it's on. So it's up to 600, go to high speed, it's at 800, and the power also changes as well. So the oscillate or static doesn't actually change the values, but and then I can sit here and it's in the powered state. So if I turn it to the, if I remove power, this box is unchecked because it is unpowered, and then our power and RPM go to 0. And then if I put the power back on, so if I plug it in, looks like we do have an issue here where it doesn't automatically put the power to that 800 value, and, or I'm sorry, the RPM to that 800 value and the power to the 55 value. So we're going to have to fix that moving forward. But if we go ahead and just change it to the medium speed, you'll see that that value does work. So interesting that while I was running this, we found an issue. So this isn't exactly a problem that we would need to solve during refinement. So the RPM, power, and powered value properties are associated with the fan structural block. And so if you run just like this without context, so not with the context, then what's going to happen is you're not going to have the ability to see the RPM and power change as you switch states. So if I go to the powered, so I plug it in and then go to like high speed, there's no way to see the value properties anywhere. So you have to associate the behavior to the structure in order to get all that to work. Additionally, if I'm trying to go and figure out these entry behaviors, I can just pull up the states, and you got the owned element, but more specifically, if you scroll down, you'll see the entry. So within the entry, so you have entry, do, and exit. So here's the exit. You also would have a do if you, do activity if you type it in. But what's going to happen with the entry activity is every time the state is entered, so basically whenever the high speed signal is sent to change from state 0 to state 3, upon entry of state 3, this RPM will occur. So I can select that in the containment tree and see where it lives. And this is an opaque behavior that I created. And how I created it was just changing the language to built-in math and then simply having an if statement. So if powered equals true, then change the RPM to 800. Otherwise, the RPM should be 0 because it's unpowered. And then the power, if powered equals true, then the power should be set to 55. If it is unpowered, then set to 0. So that's a very, very, very simple opaque action. Note that in most cases you would have something more complicated than this. You would have a whole activity diagram or any of the behavioral types of diagrams here that you would use in the entry, do, or exit criteria. So the opaque action is just another option that can quickly change value properties for you for the fan. To create the opaque behavior in Cameo, you just right select create element and then start typing opaque, and then you just select opaque behavior, and then you can just give it a title, and if you want to add it to a state, you just hit enter on that state and it will bring up the specification window, and you can type in entry or do or exit, and then you can just drag it to here, or you can create your opaque behavior here. That would be a new one. I'm not going to create a new one. I'm going to just use this one that I've called make, and it automatically moves it to the static location, and then you can see it right there. And the reason why it's blank right there is because there's no text within there. So if I wanted to go add something to the body language, I would just say hello world and then close that, and then it would say hello world there. So I can just delete that. And a way to create these partitions right here is you go to right underneath state, you have orthogonal state. It may show composite state as a default, but if you go to orthogonal state, you'll see that it will automatically populate with 2 different regions that would happen in parallel. If you want to have 3, like this one up here, you just right click the space and then go to add new region. And now you have 3 different regions instead of just 2, and you can remove the regions as well, and you can select which one you want removed. So that's how to do that. When you're trying to make this more complicated, you're going to go from an opaque behavior to probably an activity diagram, and so we will show you how to do that. So we're just going to make this opaque behavior that you see here. Alt B will show you where it is in containment tree. It's a shortcut, and so we're going to make this into an activity diagram so that you can build it out more. So we're just going to right click, create diagram, activity diagram, and we're going to call this activity diagram powered activity. And we're going to just start it off with the initial node, and we're going to find an opaque action, and we're going to use powered equals true here. So it's the exact same text that was in the opaque behavior that we're putting here. And remember that we got to go into the body language and switch that from English to built-in math. We also need to change this to a lowercase t to match the exact text from the opaque behavior. So now we connect this up like this, make it a little smaller just to help with readability, and go back here, and I'll just add this view to this and restart it. So now we need to add the powered equals true, powered activity as the entry behavior. You see that the powered activity is here as well as in the containment tree in this position. And now we can run this state machine and push run. And then when I plug it in, you'll see that this activity is run. And then this changed to powered. So it did work as intended. So we'll turn it off, or we'll remove power, and we'll just do it one more time. So be sure to look at the powered Boolean down here. So when I plug it in, you see that it turns to true because that. So essentially, as these opaque behaviors get more and more complicated, it's going to be more necessary to create more logic within an activity diagram rather than just an opaque behavior. So this is kind of your entry to convert from opaque behavior to a activity diagram. Now we'll go ahead and refine this option 2 some more. So I'm running with context, and we noticed that there was an issue last time, and that issue was when we moved to any of these states, 3, 2, or 1, and then we powered it on by plugging it in, notice that this is still at 0. It should be at RPM of 800 and a power of 55, but that's not what's happening. So you can, change it to medium state and then back to the high speed, and it'll see the correct things. So that's not the issue. The issue has to do with this plugging in and removing power. So if I remove power and then I plug it back in, notice that it's still at that 0. So how do we fix that? What we can do is, there's several different ways to fix it, but here is the opaque behavior for this high-speed state. And I will create just a holding tank just to hold it briefly. So I'll just drag this up here. The act of dragging this up here removed it. So now there's no state, or there's no behavior associated with state 3. And I can just drag this back on here, and I can click do activity, and it actually created this activity. Within here we have this call behavior action, which is this right here, which is calling the opaque behavior that it needs to call. So one last clever thing is we can just put this merge right here and get the arrow to go back to the merge. So now, and we can name it if we want to. And you can probably fill that in to make it understandable as well. But what we'll do is we will go to the medium state and then go back to the high speed state, and you see that it's still working. And now when we turn it off by removing power and then plug it back in, may have to restart the simulation. Yep, so there we go. It's just continuing to go over and over again. So that's what it's doing, is it's just continuously in this activity 3. And remember, within activity 3 we have, it's doing that RPM, and it's constantly just going to this 0 because the power is false. So now if I plug it in, and you'll see that it does change. So now this one works, but the other two do not work. So you can modify the others accordingly. Another way to solve this problem is if you use a transition to self, and then you can add the plug-in signal on the transition to self. So if I run this, we will go to high speed, and then when we plug it in, two things occur. we go from the unplugged state to the powered state, and then we also go back to start over this state, which is going to reset those values because of the entry condition. So you can scale that as well to the other states. I'll leave you with one more solution that I still have not figured out. So hopefully you guys can figure it out and let me know in the comments. And that is, if you go back to oscillating fan number 1, and instead of having the plug-in transition go to the powered state, you can bring it down to using deep or shallow history. I'm just using deep history here, and transition to the deep history. So what that will do is when I plug it in, I go to the off state just as intended, and I go to low speed, medium speed, and then I remove power, then I add power back, and you see that it returns to that medium speed. So we think we can claim success here, but not really, because it doesn't actually do this orthogonal state down here. It just does the top one. So for example, if I go to static and then remove power and then add the power back, it goes back to the oscillate. So that's not what we want to do. I've tried adding multiple histories with no luck and restarting it. I've also tried this fork horizontal and trying to send this down here. This gives me an error on the console that says the fork pseudostate is not supported in the execution. So that won't work. I've tried having 2 different transitions, both with the plugin signal attached, and that also does not work. It only uses that one plug-in transition. It doesn't actually use that other one. If I delete this one, it will use the other one. And it will remember to go back to the static, but I can't make it go back to the history for both of the orthogonal states at the same time. Let me know in the comments. Thanks.